Building motion models is fun, but they're not much good unless we use them to actually predict the future. So we're going to look at our sample problem, and we want to predict the future. The future is Justin's going to get eaten by a monster, and we want to know how far will the bus be, how far from Justin's truck will the bus be when the alien monster reaches the truck in the future. Okay, so that's the idea. We're going to use our motion model to predict the distance from Justin's truck to the bus when the alien monster reaches the truck. Okay, so recall that we start with a meaningful sketch. Take away, okay, so now we don't really care about Justin or the monster. We just have M, J, and B. And it captures the essence of all the motion stuff that's relevant from the problem is described in this meaningful sketch. That's why it's meaningful. Then we use that to build our motion model. Next, we're going to build our graph so we can kind of visualize on the graph what's happening. Okay, so here's our position versus time graph. Notice no numbers. This is qualitative. Also, look at even the title, XT. I don't even write versus T. We even call them XT graphs. Anyway, this is your qualitative position versus time graph. Qualitative doesn't mean fancy. Quantitative are the fancy ones. Quantities are the ones that have numbers and units, and we can get real information. This is information too, but it's just the quality of it. All right, here we go. We got to figure out what's going on. So I see bus is fastest. Monster's going negative. We got our positions. The bus is going to start at the origin. So the bus is going to start here. And the bus will be red. Then Justin's going to be green. He's going to be about 75. Where's 75? I don't know, but 195 is going to be about here. So we're going to make 75 there. That's Justin. And then the monster's going to be at 95. It doesn't have to be exact, but I wouldn't want to put the monster right there, right? Because that's too close. So a little bit more than halfway. I mean, a little bit more than double. All right, so now let's put Justin. Well, let's do the bus. Let's do the bus. Okay, so the bus is going at some speed. It's going to be going fastest. And there's the bus. All right. Justin is going a little bit slower, so you can see that, well, let's just see what we're going to see here. So going a little bit slower, so not as steep, right? This would be going just as fast. This is a little slower, and it's just qualitative, so it's, oops. Okay, well, I'm glad I made it in different colors. There's J for Justin. Okay, now the monster is coming negative, right? Negative velocity means negative slope, and not going as fast. And okay, now on these graphs, do we have to show what really happens when Justin and the monster meet? I mean, their cars are going to stop, the monster is going to attack Justin. I mean, so you might say, well, their lines don't continue. Well, we always just continue them. If you want to stop it, you can really stop it. But I just go ahead and continue it. Okay, so now how can we use this graph to begin to think about how to solve the problem of how far from Justin's truck will the bus load of fans be? Okay, well, we have our position equations. So if I knew the time at which this was going to occur, I could figure out the position of Justin's truck. If I knew the time when this was going to occur, monster meets Justin, I could figure out the position of the bus. And so the distance between the Justin and the bus would just be the distance between these two positions. So what I really, really, really want to know, the heart of this problem, is time. When will Justin and the monster meet? Because then I just plug the time in and I get my respective positions, and I get the distance as the difference between those two. So what does that look like on the graph here? Well, This is when Justin and the monster have the same position. If we draw a dashed line down to the, and this is not something you have to add to yours, this is my way of thinking, then this is going to be time at which they're going to meet. So this is what I'm after. Okay. Well, let's think about it. What do we know at T meet? We know that the monster and Justin are going to have the same position. So let me just draw that over there. Again, this is not something you have to add to your sketch. Okay, that's what it says, sketch. There we go. All right, because that's going to kind of help me begin to think about how to solve this problem. How do I get time? All right, so that's the idea. The key step here is solve for time to meet. So I'm just going to call that T meet. Okay, well, let's look at our equations. I want to know when the monster and Justin are going to meet. The bus we're going to forget about for a while. We don't care about what the bus is doing until we know the time. So just don't forget that's there. All right. So I've got two equations and I've got two unknowns. This is a system of linear equations. There are various ways you can solve a system of linear equations. However, I'm going to do what I think is the most physicsy way, which is kind of like the most related to the real physical world if this was a real problem. All right, and here it is. And it's all about this. When Justin and, let's imagine, here's two cars. When this is the monster car, and this is the Justin car, truck, and they're coming towards each other. And, okay, I know in the real world, Justin would swerve, or he would slow down, or he'd speed up, or do some evasive maneuver. We're in the world of one dimension, constant motion. So, sorry, Justin, you are not going to get out of this. They are going to meet at some point. That's the time that I want to know. Okay, so the time that they meet. Well, what's happening at the time that they meet? At T meet, at the time they meet, what can we say about their positions? They have the same position. Or we can say that position of monster equals position of Justin. And so that's what I'm going to base my solution on. This is not the only approach. This is the approach I use. You can use a different approach if you choose. But however, if you're not invested in that other approach, I think you should just do it this way. All right, so the key step in solving for T meet is to recognize that passing or colliding, the time that that's going to occur is, we can say, and only at, but at T meet, and only at T meet, is this a true statement? The position of the monster is going to equal the position of Justin. Why do I say it only T meet? Well, before this time of meeting, they don't have the same position. They're getting closer and closer and closer, but they don't have the same position. And again, in this scenario, if these were like just two cars passing, which is really, then they would continue on in their respective directions and they would get further away. But at this one unique time, we can say that they have the same position. Okay, so that's what we're saying right here at time meeting. So what we can do then is we can say, well, if their positions are the same, then we can set their two position equations equal to each other. And that way we'll only have one variable, one unknown. So we're going to do that. Now I'm going to do something that may shock you. I'll just do it and then we'll talk about it. Check this out. See if you find this shocking. Okay, I think you should be shocked because what am I leaving out? Units. Why am I leaving out units? I thought I was like the unit fanatic. Well, I am generally. And I always am when it comes to like, what is your motion model? When I say, what is your motion model, you must always include units. But when we use our motion model, what I've realized is over the years is that students find the math to be much more straightforward looking if we drop the units. So after years and years of resisting, I said, fine, drop the units. Okay, because then you can see that the math is not so, it's pretty straightforward math, right? We're solving for t, so this is what we're going to do. So basically, I'm going to gather up all the t's on this side. I know that makes it negative. I'm going to put all the numbers on that side, which they're really quantities. But okay, so this is going to be negative 22 t. I'm not worried that much about sig figs, although I am a little bit focused on sig figs, but I don't want to dominate here. And then this is going to be negative 120. I've already solved this, so I'm just copying it. And then basically divide both sides by 22, and then we get t equals 5. Let's see, is it still in my calculator? Okay, well, let's put it in my calculator. Okay, there it is. That's what I got in my calculator. Okay, so when I say I don't care about sig figs, I mean I care a little bit. I don't write all that down. That's way too much. Now, sig figs, we got about 2 sig figs, so if this was our final step in the process, we would want to write 5.5. But this is not the final step. This is an interim calculation. So we don't want to round off completely until we get to our final answer. So let's take a couple. So it's really be 5. What we're going to do is we're going to carry forward a couple of extra digits until we get to our final result. Then we're going to trim to meet the sig fig thing. So there we go. That's not the answer, but that is the absolute key step of getting to the answer. Okay, the next step is, what are we trying to figure out again? How far apart are Justin's truck and bus when Monster meets Justin? So how far apart? So step 2 is going to be calculate, find, get the position of Justin and bus at t equals 5.455 seconds. Okay, so basically, again, when you're working with your model, you don't need to include units. When you publish your model, you must include units. So basically, where's Justin going to be? Justin's going to be at 16 meters per second times 5.455 seconds. We put that in a calculator, and we say times 16 and position of 87.27 meters. 87.27 meters. Does that make sense? We should always be thinking, do our calculations make sense? Yes, he's getting further. Well, something doesn't make sense. I'm going to pause the video and figure out what the heck I did wrong. This is why we check to see if things make sense, because this makes no sense. This makes no sense. Justin Bieber, and I realize that's how I caught my error, because I forgot to add plus 75 meters. So we need to add 75 to that. So we're going to add 75 to that, and we get 162.27. Okay, 162.27. This is where Justin's going to be when he meets the monster. Okay, that's not the final answer. All right, where is the bus going to be? Okay, see, that's why we check for reasonableness. All right, the bus is going to be, starts at the origin, so we're going to take the bus's velocity, 22 meters per second, times 5.455 seconds. I probably didn't need that extra digit there. And we get 22 times 5.455 equals 120.01 meters. And so how far apart are they? This is the final answer. So distance between, and we're going to take basically Justin is at 162.27 meters minus 120.01 meters. I know this is kind of small here, but all right. So I've got 120. I'm just going to go ahead and minus from that 162.27. I know it's going to be negative, but the absolute value of that is the distance. So, all right, now what do we trim? So the answer is distance between equals, let's round that off to 2 sig figs. Okay, so 42 meters. So the bus, fortunately, I think they're going to be far enough away where they won't see the carnage, but not sure about that. All right, this is what I'm looking for when you solve. So what do I want to see when you solve? So if you need to solve for the time that passing, or so in terms of like showing your work, certainly that and this, you don't have to show that much in the middle of the road algebra. So basically, I want you to show your work. Show your work, show your work, okay? This is a sample problem. This is what I'm looking for. Something like this.